Okay, right, so before the break, talking about gases, we did a day where we did basically just calculation, calculation, calculation. And if you cast your mind back, there was a point where we realized that, except for one time, it never said in the question what the gas was. It's only one time that it said in the question what the gas was, and that was so that we could calculate the number of moles. Every other time it just said, I've got a gas, it's in a box, the box is this big, it's at this temperature, tell me what's going on. And that's because gas behavior is really dictated by this. That the distance between the particles is so much larger than the particles themselves that when this one bounces and that one bounces to create pressure, they're independent of each other. So it doesn't matter what the gas is. It doesn't matter. A mole of any gas occupies the same volume. Don't expect anybody to remember what that volume is, but if somebody did, it would be spectacularly cool. 1 mole of gas occupies how much volume? 22.4 liters. Good job. Any gas. So it doesn't matter what these gases are. This is gas A, and that's gas B. They could be 2 different types. They're each creating their own pressure. So Dalton comes along and he sees this and he says, all the math works whether it's a pure sample or whether it's a mixture. And all I have to say is how many of these particles do I have and how many of those particles do I have? And that's it. That's what we're going to do today. Dalton's law of partial pressures says that the total pressure exerted by a mixture of gases is the sum, just add the numbers together, of the individual pressures of the gases. Now, because these individual pressures sum to make a total, Dalton calls the pressure exerted by A and the pressure exerted by B partial pressure. And when you add the partial pressures together, you get the total pressure. So the total pressure exerted by a mixture of gases is the sum, add them together, of the individual partial pressures of the components. Okay. And you can do this for very simple mixtures. You can do this for very complicated mixtures. It's all the same. So if I had a mixture that was A, B, and C, the total pressure would be equal to the pressure of A plus the pressure of B plus the pressure of C. If I had a fourth gas in there, D, I would be adding the partial pressure of D onto it, okay? So however many components you have, just add them up. Now these are pressures in their own right, but we can't see them because they're part of the total. So these get a little apostrophe. And in chemistry, or in science, in physical chemistry, having an apostrophe as part of your title means I'm not quite finished with this number yet. But this number is going to be used to find another number. So those are the partial pressures. Okay. All right. PV equals nRT. Today we're going to be using PV equals nRT to find P. We're not going to be interested in volume or temperature today. We're going to be looking at a pressure. So I'm going to rearrange PV equals nRT to tell me P equals nRT over V. Okay. Now the volume that A occupies is the same volume that B occupies, is the same volume that C occupies, because they're all in the same container. So the volume in the question is the size of the container. Gases fill their container entirely. T, the temperature of A, is going to be the same as the temperature of B, which is going to be the same as the temperature of C. They're all at the same temperature. R is a constant, and it's a constant for all of them. It belongs to all of them. But number of moles, well, each of these has their own number of moles. So there's a couple of things that we can say here. We can say that P total, the total pressure, is equal to the total number of moles. Yeah. Guess what the pressure of A is equal to? Shouldn't be too much of a stretch. Number of moles of A, RT over V. And the pressure of B is going to be the number of moles of B times R times T divided by V. Okay? So the more of this I have, the more moles of A as a component I have, the more it expresses its pressure. That makes sense. And the total is just all the values of N added up. Okay? So for here, the total number of moles is just the sum of the numbers of moles added together. All right. Okay. So it turns out that when you are asked a question about Dalton's law, it usually comes in two parts. It usually comes in two parts, and it asks, here's a mixture of gases. What's the total pressure? And then it usually asks, and what's the pressure of one of the gas components? What is it contributing? Okay. Turns out there are two ways to do this question. And the way that I do it depends on in which order the question asks what it asks. Because if it asks me, first of all, to find the pressure that belongs to one of these components, let's just say it picks out B, component B. I want to know what the pressure of that gas is in the mixture. Well, then I do this kind of thing. I just pick one of the gas moles out. And then when it asks me to find the total, well, then I'm going to go and find all the number of moles of all the rest and then throw those in here. But when it asks me the same two questions, but in a reverse order, I answer this question differently. If it says, find the total pressure as the first part of the question, that means I have had to have found all of the numbers of the moles. So I've got those written down somewhere. They're on a little, in a side table somewhere, because I have to find each of these numbers of moles, and then I find the total. And then when it says, now go ahead and find the pressure of the components, I can either slot those numbers in, because I already have them, or I can do something else. I can do something else. The total is made up of these numbers, right? What if, and then look, the pressure, R is the same, T is the same, V is the same. So the only thing that's making pressure change is the number of moles. What if my mixture was 90% this, 5% of that, and 5% of that? Wouldn't the pressure of this just be 90% of the total? Yeah, yeah. So if you know what the percentage of your moles are, then you don't have to have five terms in your calculation. I don't need a P and an N and an R and a T and a V. I can just say P is the percentage of the total. And it gives me 3 terms instead, okay? So this is what it looks like. The partial pressure of A is equal to something that we call the mole fraction. Mole fraction is a chi. It looks like an X. It looks like a tall, skinny X, but it's actually a Greek letter. Because R and T and V don't change in any of my calculations, pressure is directly proportional to the number of moles. This is a percentage, but instead of going from 0 to 100, it goes from 0 to 1.00. It's just like a percentage. This is like a percentage, but goes from 0 to 1.00. Instead of going to 100, it goes to 1.00. So you know what percent means, right? It literally means divide by 100. So 99%, take your 99 and divide it by 100, and now you've got 0.99. So it really is, it's just like a percentage. And all that is, XA is the number of moles of A divided by the total number of moles. If we were going to write this out as a percentage, we would write times 100% here, and then that would be a percentage. But we're going to keep the number less than 1. Okay? All right, I'm going to throw some numbers up on the board, just at random or almost at random. And then we'll work through finding the total, finding one of the components, and then we'll fact check that our numbers are right 2 different ways, one of which will be with a mole fraction. Okay? All right. Questions about this before it all comes off the board? Okay. Okay, let's have a question. I have a vessel. It has a volume. It contains, let's give it 2 gases. What should we have the first gas be? Oxygen. Give me a gram amount of oxygen. Okay. I need a second gas. Argon. That's what I think I heard. Argon, good choice. How much? And I need a temperature. Let's have the temperature. Somebody. Cool. That's boring. Yawn. Give me a temperature that's not room temperature. Who? 180 degrees. This is going to be a big number. Okay. All right. All right. There's a gas. It's confined to a vessel. I have 2 grams of oxygen. All right. Each oxygen atom in a molecule of O2 has a mass of 16 grams per mole. So that's a small number. That's 0.2 divided by 32. That's less than a mole by a lot. Remember, 1 mole wants to occupy 22 liters, 22.4 liters at room temperature. At an elevated temperature, wants to occupy a lot more space. We don't have a big container. We've got a small container. So it's going to be pressurized. Whatever this answer comes out to be, it's going to be pressurized. And then I've got 7 grams of argon. Argon has a mass of about 40, so 38 point. I have to go closer to read it. So still less than a mole. But then the kicker is we're doing it at an elevated temperature. So the pressures that I'm expecting to come out of this are definitely going to be in 2 digits, possibly higher. All right, question 1. Find total pressure. P B equals nRT, which means that P total is N total RT over V. Before you just go throwing numbers at this, give yourself a table. Figure out, do you have all the information that you need? And is it in the correct form? Pressure, well, that's the number that we're looking for. Volume, well, that's the size of the container. And we only have 2 significant figures here. I got 2 here, I've got 3 there. So let's give this, previously I only had 1 significant figure. So that's not going to give us good enough. That's 500.0 milliliters. Okay. Total number of moles, got to figure that out. And then R. R is a constant. 0.0821 liter atmospheres per mole per Kelvin. And temperature is 180 degrees Celsius. Okay. Have a stab at it. I'll let you have a couple of minutes. Have a go at it. And then we'll kind of see how far we can get. And then we'll look around ourselves and figure out if our neighbors can help. And then we'll throw it all up on the board. Total number of moles is the number of moles of oxygen and the number of moles of argon. right, if you got to that point where you can't remember how to find the number of moles, how do you find the number of moles? Moles equals mass divided by formula mass. It should be kind of a mantra by now. We're going to say that a couple of 100 times before the semester is over. Moles is mass divided by formula mass. So this is the mass of oxygen divided by the formula mass of oxygen, and this is the mass of the argon divided by the formula mass of the argon. And the argon is 39.94. 40.
Like if it was like.
Each of these oxygens is 15.99 grams per mole. Let's call it 16. And you've got two of them, so that's 32 grams per mole. So the numbers that go here, 2 grams of oxygen divided by 32 grams per mole. That's the number of moles of oxygen. And I do that for the argon. Here's the mass of the argon. That'll give you two numbers. Write those numbers down independently of each other because you're going to need them later. We haven't seen the question that's coming later, but you've been told that in all likelihood you're going to be asked a question about one of the components. Write those down and then sum them. Okay. All right. Let's have these numbers on the board, and then we can look at what we need to do next. What is this number? Okay. And what is this number? Yes? Did I write down that correctly? Yeah. Okay. All right. So the total is this number plus that number. Add those two numbers together. And that gives me N total. It's just 24, isn't it? Mm-hmm. Okay. So all the numbers are on the board. Do we just go diving into putting them into PV equals nRT? No. Hold on. Why no? So when I went to the textbook, you didn't see me go to the textbook, to get this value of R, this value of R only works if my volume is in liters. Is my volume in liters? No. No. No, it's not. So I have to change the volume. It works if my pressure is in atmospheres. Is my pressure in atmospheres? Well, we haven't found it yet. So when we do find it, it's going to be in atmospheres. And if you're okay with that, then we can continue. And my moles have to be in moles, which they are. And my temperature has to be in Kelvin, which it's not. Okay. So I have to do the conversion that converts. I'm going to make it a little bit smaller than that. Converts milliliters into liters. And in order to do that, milliliters needs to go on the bottom so it cancels, and liters needs to go on the top. So I need to know how many milliliters are in 1 liter. How many milliliters are in a liter? It's always 1,000. The answer is always 1,000, week 1. $500 divided by 1,000. It's 0.5. All right. That's a high temperature-ish. What do I have to add to turn that into Kelvin? 273. Go ahead and add 273 to that. Okay, now put the numbers in. Put the numbers in and see what you get. Okay. If you're starting to come up with an answer, share that answer with the people close to you to see if your number is in the same ballpark as their number. And then we'll see if that number makes sense. So total pressure is the total number of moles, which is 0.243, okay? A quarter of a mole-ish. 1 mole would want to occupy 22.4 liters. A quarter of a mole would want to occupy a quarter of that volume, so about 6 liters. And we don't have 6 liters. We have half of a liter. So this is going to be pressurized. Expect this to be pressurized. And then we get to the part where, hold on a minute, that 22.4 liters was at room temperature. This is an elevated temperature. So the R is 0.0821 liter atmospheres per mole per Kelvin, and then the temperature is 453 Kelvin, and the volume is liters, half a liter. That liter cancels with that liter. This mole and that per mole cancel. This Kelvin and that per Kelvin cancel, which leaves the only thing standing, atmospheres. Which means when all of these numbers do what they do, we should have a P total. And what was that number? 18. Okay. Agreed? Yeah. All right. 18 atmospheres. So here's a container. This is only a quarter of a liter, not half of a liter. I've got to stick 18 times atmospheric pressure into here, which means I need to clamp that cork down on this. Otherwise, it's going to just pop off. Am I worried at 18 atmospheres that this glass is going to break and kill everyone in the room? No, not at 18. It goes higher than that, and I start saying, I'm glad I did the calculation before I did the experiment, because that's too high for the safety equipment that we've got in the room. 18 is starting to get high, but yeah, not so much. Okay. Okay. The follow-up question says, find the partial pressure that belongs to the argon. Because we've already done this work, got to slot this number in. So that was the number of moles of oxygen. This is the number of moles of the argon. This number is 3 times bigger than that number. The moles of argon is 3 times larger than the moles of oxygen, which means this 18 atmospheres of total pressure belongs mostly to the argon. Most of it belongs to the argon. So when you get a number, and that number doesn't come back to reflect that little piece of logic, do your math again. The pressure of the argon is the number of moles of argon times RT divided by V. None of these numbers have changed. The only number that's changed is the number of moles. So because I've got all of that still written on the page, all I have to do is refer back to it. And the number of moles of argon is 0.18. What's your value? 13. Does anybody else agree? Yes. Okay. I haven't done this math, but I did the little bit of logic before you did the math that said this is 3 times bigger than that. So this should be representative as much, much larger than the oxygen to here. So there you go. These mysteriously turned into partial pressures because that's how they're defined. Okay, with a little apostrophe. All right, so we found the total and we've found the pressure of one of the components. What we're asked to do next is find the other number. Well, the other number, there's 3 ways of finding that other number. Let's do at least 2 of them. If the question then says, find the partial pressure of the oxygen, there are 3 strategies to get to that number. The first is to say that the partial pressure of oxygen is the number of moles of oxygen. It's a good thing that we've got that written down. And then just to do PV equals nRT all over again. But that's surely too much work. Because one of the other strategies says, what? If we could write Dalton's law of partial pressures, so this is coming off the board. You can do it. That's strategy number 1. Keep it, do it. I'm not going to figure that one out because that's got like multiplying and dividing in it. And 5 terms. If we could define Dalton's law of partial pressures in terms of a single equation, what would that equation read like for this particular experiment? Yeah. Now, correct me if I'm wrong, but don't we know that number? And don't we know that number? So doesn't that mean that we know what this number is as well? Yeah. So this was 18. This is the number that I've been told to go find. And this was 13. So go figure. What number, when you add it to 13, gives you 18? Yeah. P02 is P total minus PR, which is 18 minus 13, which is 5 atmospheres. Okay. I learned how to do that in elementary school. I learned how to do PV equals nRT in high school. This means this one is more error-free than the other one. So given the choice of which of those 2 I do this one. Total is the pressure. And that pressure, the total is the sum of the partial pressures. That is Dalton's law written down. And then we just use arithmetic to get to the answer. Okay. Let's use the mole fraction. If the question becomes not only go find the number, but I'm going to tell you, going to restrain you and tell you how to find the number. Find the partial pressure of oxygen using partial pressures. Nope, we've already done that. Using mole fractions. Finding the value of oxygen. If you did the PV equals nRT, it comes out to be 5. If you do P total is partial pressure of 1 plus the partial pressure of the other one, it comes out to be 5. When you use the mole fractions, it had better come out to be 5. So this is a way of going back at the end and checking that your math is valid. Okay. I need space, so I'm going to have to erase this. We're still writing, so I'll give you a minute. Let's think. I have two values. This one is 3 times bigger than that one. My total is 18. And what I'm going to do is I'm going to take this number of moles and divide it by the total number of moles. The total number of moles is this number of moles and that number of moles, which is the number that's in the box. Okay. Use that as a percentage. And this is basically just asking the question of what percentage of the total does this number of moles generate? So the equation says that the partial pressure of oxygen is the mole fraction of oxygen times the total pressure. This is the number of moles of oxygen over the total number of moles. So this gets to be 0.063 divided by 0.243 times 18. This is in atmospheres. These are both in moles, so they cancel. What's that answer? I'm guessing it's 5. There are many, many different ways to get to the final answer. You are allowed to pick whatever way you want. Bear in mind, sometimes the way that you want to do it is not going to be the easiest. Okay? All right. I'll see you all on Wednesday.